Welcome to the first lecture in linear algebra series. We all deal with the tables of numbers, mark sheets, images, timetables, networks. Instead of looking at them as a scattered data, we can represent in a powerful and a compact way by using matrices. So in this lecture, we will be discussing what is a matrix and the basic operations on matrices. So what is a matrix? Matrix is a rectangular array of numbers or expressions arranged in rows and columns. Suppose if someone says the matrix is of size m by n, that means there are m rows and n columns. An example of 2 by 3 matrix is given here, where we have 2 rows and 3 columns are there, and every row contains 3 elements and every column contains 2 elements. So we will refer an example here. We will refer ith row and jth column element as a of ij, and some special types of matrices. So in a matrix where we have the number of rows is equal to the number of columns, then we call that as a square matrix. In a matrix where you have first row first element, second row second element, third row third element, so on, that we call it as a main diagonal elements. A matrix, a square matrix where all the non-diagonal elements are 0, that matrix we call it as a diagonal matrix. And if the main diagonal elements are 1 and the remaining elements are 0, that we call it as an identity matrix. Here an identity matrix of size 3, that is 3 by 3, and we have a triangular matrix. It might be an upper triangular matrix or a lower triangular matrix. All the elements below the main diagonal are 0. That we call it as an upper triangular matrix. And similarly, for all the elements above the main diagonal, all the elements above the main diagonal are 0. That we call it as a lower triangular matrix. Here you can see that the identity matrix is both upper triangular as well as lower triangular. And what are the basic operations on matrices? Addition and subtraction. Addition and subtraction can only be performed if the matrix are of the same dimensions or the same size. Now, simply you will be performing an element-wise operation. If you want to perform addition of two matrices, simply do element-wise addition. Like here you have two matrices, A 1 2 3 4 and B 5 6 7 8. Then 1 plus 5, 2 plus 6, 3 plus 7, 4 plus 8 gives you the addition of two matrices, that is A plus B. Similarly, subtraction and the scalar multiplication. So multiplication matrix by a scalar. So each element of the matrix should be multiplied by that scalar. Suppose if you want to perform some C into A, where C is a scalar, so an example 2 and a matrix is 1 2 3 4, you multiply every element by the scalar, you get the resultant for C into A. That means 2 into 1, 2 into 2, 2 into 3, 2 into 4, and whatever the resultant matrix is C into A. And the next operation is the matrix multiplication. But to multiply matrices, two matrices A and B, the number of columns in A, that means the number of elements in each row of A, must be equal to the number of rows in B. That means the number of elements in every column of B must be equal. If you have two matrices, one A is of size m by n and B is of size n by p, then the resultant matrices that you will get of size m into p. To get an ith row and jth column element of A into B, we just have to do a dot product of ith row of A and a jth column of B. We will see an example here. So here, to get a first row, first column element of A into B, we have to take the first row of A, that is 1, 2, and we have to take the first column of B, that is 5, 7, and do a dot product, that is 1 into 5 plus 2 into 7, which gives you first row, first column element of A into B. Similarly, to get the first row, second column element of A into B, so just take the first row of A and the second column of B and do a dot product, that is 1 into 6 plus 2 into 8. So if you perform this, then you will get the resultant matrix A into B. Now some basic properties. One of the important properties that you have to keep in mind is matrix multiplication is not commutative. A into B is not necessarily equal to B into A, and it is associative. A into B of C is A into B of BC, and it is distributive over addition or a subtraction. A into B plus C is AB plus A into C. And you can check with an example here that B into A is not necessarily equal to A into B. So we have A into B, we got this, and B into A, we got a different value. So not necessarily it is equal, and it is not commutative. Now we define something called a trace operation on a matrix. So trace is defined for a square matrix. It is a sum of the elements of the main diagonal. As we know, the first element, the first row, first column element, second row, second column element, third row, third column element, fourth row, fourth column element, so on. Those are the main diagonal elements. If you add all those, then it becomes a trace. Now trace of A plus B is trace of A plus trace of B, that you can easily see. Trace of C into A is C into, because as it performs element wise, you just have to take C as a factor from that addition, because addition is multiplication is distributive over addition, so you can see that. So even though it is, the matrix multiplication is not commutative, trace of A into B is trace of B into A, because just the order of the multiplication changes. And the next operation is determinant. Now to determinant is a scalar value, so that is computed by considering all elements of that square matrix. So it is very useful in calculating the inverse and solving some system of equations, and doing and interpreting the transformations, some linear transformations. Now it is denoted by using a mod A or det of A. Now let us try to understand an example of determinant of a square matrix, 2 by 2 matrix. Now the determinant of A is A into D minus B into C. For this example, 3 into 2 minus 4 into 1, so we will get 2. So how we are going to calculate determinant of a matrix is by using minors and cofactors. First let us define what is minor. So minor is defined for an element in that matrix A of ij. We have to take the determinant of a submatrix by deleting the ith row and jth column of that matrix. So just for whichever the element you are calculating the minor, just let us consider that element as A of ij. You remove ith row and jth column from that, and remaining elements you consider it as a submatrix, and for that you find out the determinant, and the cofactor is that minor multiplied by the some sign factor, that is minus 1 power I plus j, that gives you a cofactor. And if you write cofactors for every element, you can find the cofactor. So if you write all cofactors of all the elements in a matrix, then it becomes a cofactor matrix. Now the determinant can be calculated by using a cofactor expansion method. So here you find consider the first row a11, a12, a13, and for each element you find the cofactors. So for a11, let us suppose the cofactor is c11. So how are we going to find out for a11 the cofactor c11? So first remove the first row and first column, and the remaining sub matrix is 4, 5, 0, 6. For that you find out the determinant and then add a sign factor minus 1 power 1 plus 1. It gives you the cofactor, that is 24. Similarly, you can find the cofactor for the remaining elements. For the you remove the first row and the second column, then you will get a submatrix 0, 5, 1, 6. For that you find out the determinant and add a sign factor, that is minus 1 power 1 plus 2. Then if you use this cofactor expansion method, just multiply with that respective element for that row, then you will get the determinant. So as you can see that in a cofactor expansion method, we are going to use a particular row or a column elements. If a particular row or a column elements of a matrix all are zeros, then the determinant is 0, and the determinant of an identity matrix is 1, and the determinant of A transpose, that means if you just change the rows to columns and columns to rows, then the determinant remains same. And if the two rows or columns are interchanged, the sign of the determinant also changes. And the determinant of A into B is determinant of A into determinant of B, and determinant of A inverse is 1 by determinant of A. Thank you.